Welcome to qnawire.
Now, since in this problem all the forces and torques are internal to the system, therefore the angular momentum will be conserved in the Earth asteroid system, which means that the initial angular momentum will be equal to the final angular momentum. And L here is the total angular momentum for the Earth and asteroid system. And we know that angular momentum, the magnitude of angular momentum is can be written as I, which is the moment of inertia of the object, times omega, which is the angular velocity. So for initial case, we write I of Earth times omega of Earth plus I of asteroid plus omega of asteroid, and these are the initial angular velocities for Earth and the asteroid respectively. And for the final case, we have I of Earth times omega f, which is the final angular velocity of Earth, times I of A times omega f again. Since both have the same angular velocities, so we are using the same notation, and this can be written as IE plus IA times omega f. Now, assuming the Now this expression comes from the assumption that the asteroid becomes embedded in the Earth at the surface. Therefore, both the Earth and the asteroid will have the same angular velocity after collision. Also, we model the Earth as a uniform sphere and the asteroid as a point mass. This means that I of Earth will be equal to 2 by 5 mass of Earth times R of Earth square. This is a sphere, and since asteroid is assumed to be a point mass, I of A can be written as mass of the asteroid times O. I got confused with the notation. So yeah, mass of the asteroid times radius of the asteroid square. Now we have, so let's solve for the first equation now. So we have I of IE, the omega E plus IA omega A to be equal to IE plus IA times omega F. Now, if you compare this value with this value, we can say that the moment of inertia of the satellite can be ignored relative to the Earth. So IE plus IA can be taken nearly equal to I, which is moment of inertia of the Earth. So that's what we will do over here. So we write it nearly equal to IE times omega F. From here, we can write omega F to be equal to IE omega E plus IA omega A over IE. Now for the percentage change, first we need the fractional change. So for that, we need omega F minus the initial velocity of Earth, which is omega E over omega E. So this is the fractional change. And if we substitute this value of omega F over here, we will get this fractional change to be equal to IA over IE times omega A over omega E. Therefore, so this is the fractional change. Therefore, the percentage change will be fractional change times 100. This will be equal to Ia omega A over Ie omega E times 100. Now, let's use these expressions over there. And one thing to carefully take from here is over here the radius of rotation of the asteroid is in fact radius of the earth, since the asteroid is very close to earth. So these two are nearly equal. So we can write Ia to be equal to mass of the asteroid times radius of earth square times omega A over 2 by 5 mass of the earth times radius of the earth square times omega E. And we have to multiply this by 100 for the percentage change. Now we know that this over here is omega A can be written as uh, omega A can be written as R of earth velocity of asteroid over radius of earth. So we can write that. So let's use this over here, and doing that we get, so let me do this on the next page. So we simply substitute this omega A over here to get the percentage change to be equal to mass of the asteroid over 2 by 5 mass of earth. Re square, these two are cancelled, and we have V over Re for omega A and 1 over omega E, which is this term over here, times 100. Now let's write the variables that we are given, so you can substitute them into this equation. So we have mass of the asteroid to be 10 to the power 5 kg. Velocity of the asteroid is 3.5 times 10 to the power 4 meter per second. Mass of earth is 5.97 times 10 to the power 24 kg. Angular velocity, initial angular velocity of earth is, so earth covers 260 degrees. So earth makes a full rotation in 24 hours or 1 day. Now if you convert 24 hours into seconds, you have to multiply it by the number of minutes in 1 hour and then the number of seconds in 1 minute, and this comes out to be equal to 86,400 seconds. Therefore omega will be equal to 2 pi over the time period of earth, which is 860. So let me just write the equation so it will be easy for you. So this is what we will be using, and the time period for earth in seconds is 2 pi over 86400 seconds. Now let's plug these values. Okay, one thing I forgot to write, the radius of earth, which is 6.38 times 10 to the power 6 meter. Now we can plug all these values in this equation and solve them, multiplying it by 100. And if you do that, you will get the percentage change to be equal to percentage change in angular velocity after collision to be equal to 3.2 times 10 to the power minus 16 percentage. So this is the percentage by which the angular velocity of Earth has changed after colliding with the asteroid.